Okay, let's jump into the second problem, and we're going to make a table for this one as well. This one's going to get a little bit tricky, and we will start this one at 3, down here at the bottom. So 8 times 1/2 to the third power. Okay, well, 1/2 to the third power is 1 cubed, that's 1. 2 cubed, that's 8. So we have 8 times 1/8, and that's 1. So what we really have is a coordinate of 3, 1. 1, 2, 3, 1. Done. Okay, now, you want to get technical? You could go ahead and plot the point 1, 3 as an inverse. It's going to clutter my graph. Let's not go there yet. All right, 8 times 1/2 squared. That's 8 times 1/4, and that is 1/4 of 8. That's 2. Okay? 8 times 1/2 to the 1, and that's going to give me 8 times 1/2. That would be 4. And you can look at the pattern and see where this is going. 1, 2, 4, 8. It kind of makes sense because it'd be 8 times 1/2 to the 0. And so I would have 8 times 1/2 to the 0, which would be 8 times 1, which of course is 8. And then here we're going to have 8 times 1/2 to the -1. And that gives me 8 times, okay, negative exponents. They move things. This 1/2 is going to get reciprocated. It's 2 over 1. 8 times 2 is going to give me 16, which means this coordinate is not going to be on the graph. Okay, -1, 16. -1, 16. Way the snot up here. I love that phrase. It's so nice. 0, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 4. 2, 2, 3, 1, 4. Why not? Why not? Why not? Why not? Why not? Why not? Because it's not on the paper. That's why not. 8 times 1/2 to the 4th. Okay, 1/2 to the 4th is 1/16. 8 times 1/16. The 16th of 8 would be 1/2. So 1/2 here, 1/4 here, 1/8 here, It's going to get closer and closer to the x-axis, but on the positive side. Notice that this one was close to the x-axis on the negative side. This one's close to the x-axis on the positive side. And also, again, we had a coordinate of -1/16, which was way up here, but nah, we're not going to talk about that one. We shall not mention him. But it does go way up there. Okay, don't cross that x-axis. There we go. All right, we can find the domain and range. Let's go ahead and do that. Let's do this a little bit out of order. So we're going to have our domain, our range of our original function, and of our inverse. Okay, original domain. Okay, let's look at the equation for this. The question really is this, for a domain. What x values can I use? I can use any x value I want. It's like I never divide by 0. I never take the square root of a negative number. We never do anything where it's like, man, you just can't plug that x value in. You can plug in whatever you want. Your graph's going to look crazy, but you can plug in whatever you want. Graphically, you can see it. Clearly, it goes to the right forever, but it also goes to the left forever. It goes up and to the left very sharply, but I could plug in -1 zillion if I wanted to, and my graph would be way up yonder, but it would exist. Okay? Even though I haven't even talked about the inverse really, I know this. Domain and range are switched. It's automatic. Totally automatic. Draw the red arrows if you like or not. It doesn't matter. But now we're going to talk about the range. The range of the original function. Let's see. The lowest it goes is 0, but not including 0. And it goes up to infinity. Does not include infinity, clearly. Which means the domain of the inverse will be the same. Okay, this graph, before I draw the inverse, which is going to be lots of fun, it's going to be a little confusing actually. You're going to see what looks like some overlap, but it's minimal. This is exponential, sorry, my mind went blank for a second there. Exponential decay. We have talked about this in a previous lesson. The graph is going down as you look from left to right. This was exponential growth. And I just want to point out that the y-intercept here is at 8. I'm just saying. The y-intercept on this one, the previous problem, is at, wait for it, 1. 1 times 2 to the x. There was an understood 1 there. So whatever, there it is. Now you can see. Whatever your coefficient is of your exponential factor. That's what your y-intercept is going to be. All right, so now we're going to draw the inverse and be done with this problem. And I'm going to start with something that's a little bit obvious. 2, 2 becomes, well, 2, 2. That was it. It's the same on both graphs, which makes sense if you draw the line y equals x. There we go. Okay. All right, look at the point 3, 1. That becomes 1, 3. Very close to the other. Let's see. 4 comma 1/2 becomes 1/2. 1, 2, 3, 4. The coordinate 1, 4 becomes 4, 1. They look like they're kind of overlapping, but they're not. And then 0, 8 becomes 1, 2, 3, 4, 5, 6, 7, 8, 0. So this one is tricky to draw. And it's so tricky to draw because it being the red graph, the inverse, does cross the x-axis, unlike the original function, but does not cross the y-axis. It hugs this corner just enough to where it's really hard to articulate which one is which. But the inverse does not cross the y-axis. The original function does not cross the x.